calculating absorption of heat questions. Now we're going to look at Q because in the previous video we looked at Q as being the amount of heat released or absorbed. And how did we get that? Because last time, again, you should see the previous video. Last time, we got delta H is equal to delta U plus pressure, which remains constant, times the change of the volume. And this comes out of the system. So let's say if this comes out of the system, if this comes out of a system, it needs to be absorbed by something else, right? It needs to be absorbed by something else. And again, and also in the last video, we looked at the something else would be the surrounding. Since delta E, so the change of energy of the system plus the change of energy of the surrounding equals the change of energy of the universe. These two need to be summed up. Depending if this one increases, then this one must decrease. If this one increases, then this one must decrease. It's an ebb and flow of give and take. If this is from a system and this is releasing a certain amount of energy, it's going to go somewhere. It's going to go into the surrounding. So this is going to release it to this. Let's have a look at delta H then. If we look at delta H, and we got it from up here, the delta H is going to equal Q. But we've established if this is the system and it's giving off energy to the surroundings, this here, let's label it as the system, then this has to be a negative value. Because if it becomes negative, it means that it is exothermic. It is releasing energy. Negative means a release. So that negative value releases that energy as indicated, and it must be absorbed by something else, the surrounding. And we're going to put Q as the variable. So Q here, if it's taking in energy, it's endothermic. It's going to take in the energy, so it's going to be the opposite of negative. It's actually going to be positive. And here we're just going to put maybe surrounding. It's just whatever is around the system. And in the practice problems today, we're going to be looking at, a lot of time it's going to be water. So the energy released is going to be absorbed by the surrounding, and it's going to now be a positive value. Now it's important to look at Q here. I know this could be a negative value. Let's say it's exothermic and it releases that energy to the Q. Q has to have a certain value that we can calculate. How much energy actually went into the Q? We have a formula called Q is equal to mCT because it really does depend on the mass of what the surrounding is. It also depends on the specific heat capacity, and it also depends on the change of temperature. How much of an increase in temperature. So in this case, it would be the increase in temperature because it's exothermic, it's giving off energy, and it's giving it to the surrounding. So how much temperature was it before, initially, and how much temperature was it after, and then the difference of that is how much temperature increased. So the amount of kinetic energy that was given into the Q, and temperature is a indicator of that, how much kinetic energy was involved. So we have to use this formula when we start solving the problems. So we understand the concept now of delta H, and Q. But now we're going to start getting into the mathematics. So if Q is equal to mCT, let's label what these are. Well, we already know what Q is, but for M, this is the mass. And for the C, this is the specific heat capacity. And what is the specific heat capacity? The specific heat capacity is the amount of heat needed, or amount of energy needed. Amount of energy needed or required to increase the temperature. I'm just going to put temp for short. Temperature of 1 gram by 1 degree Celsius. This means the higher the C value, higher the specific heat capacity, the more energy it is needed. So it's going to be a little bit more stubborn. So a more amount of energy is required, which means it's going to be more difficult to increase it because you have to put in more energy. So it's very difficult to move it. The amount of perturbation is not going to be easy to move it around. And then we have to look at temperature. This here is the change in temperature. Again, represented by the delta. On a warm day, how much solar energy does a 3.92 kilogram piece of concrete absorb as heat if temperature increases by this much? Let's put our formula first. And our mass here is 3.92 kilograms. Temperature increases from 13.60 degrees Celsius to 14.50 degrees Celsius. Well, with our temperature, in order to find the change, the difference between the final and the initial, so this here is our TF, our temperature final, and this here is our temperature initial, all you need to do is get the difference between the two. So you get 0.9. So that is our delta T. So we have M and we have T. Now we just have to find C. What is C? C is our specific heat capacity. We just have to look for concrete. And if we look for concrete, it's right over there. Okay, it's at 0.88. So it's just 0.88 joules per gram Celsius. Now here is the issue. If this is in grams and this is in kilograms, this is a disparity that we don't want. We want to keep them the same so that eventually we can cancel it out. That means we're going to change this kilogram into grams. So instead of 3.982 kilograms, it's instead going to be 3,982 grams. That's what we're going to have instead. Now let's put this all together. So we have our Q is equal to M, 3,982 grams, multiplied by the specific heat capacity, which is 0.88 joules, divided by grams times Celsius times the temperature change. Now, our value of 3,982 grams is technically over 1. Any value is over 1. So that we do that because now we have two fractions that are beside each other. Well, diagonally, with fractions, if there's a gram and a gram here, we can cancel them out because they're of the same unit. If they're the same unit, we can cancel them out diagonally. Same thing over here. 0.9 is the same as 0.9 over 1. Degrees Celsius, they are diagonal, so we can cancel them out. So then we're just left with 3,982 times, I guess you don't need to put times, we have a bracket there anyway, so 0.88. Do not forget the joules, very important to keep your units, multiplied by here 0.9, and bottom of that here just 1 times 1. We don't really need to keep it there if you don't want to, no big deal, and that's all we need to do. So let's just multiply these together. So 3,000, got my calculator out, 3,982 multiplied by 0.88 multiplied by 0.9. So then we're given 3,000 153.74. Don't forget the joules. Next question. 1 liter of water at 1 degree Celsius is warmed by the addition of 4 kilojoules of heat. What is the final temperature of the water? Remember here that 1 liter of water has a mass of 1 kilogram. How are we going to start this off? First, we need to look at our formula, at what we need to have on file here. Now, in order to solve for Q, we need to have our M value. Our M is going to be 1 liter, but 1 liter is actually the same as written here as a kilogram. So instead of liter, we can put kilogram. All right, because we're not looking at volume, we're looking at mass. So a kilogram would work. 1 kilogram, it's going to give us a problem because if we look at our chart, our specific heat capacities, the denominator is grams, so that's going to create some issues. So rather than keeping it in kilograms, let's just change it right away to grams. And then we have our specific heat capacity, and again, it is liquid water, so we look at our water, same thing, 4.19 joules per gram times Celsius. And then we need to multiply by our temperature. Change in temperature, not just temperature. Why? In the beginning, in our question, it says that it is at 1 degree Celsius. But we can't put that over here because it is warmed by the addition of heat. So it has to be an increase in temperature from 1 degrees. And if you just look at the next sentence, it says what is the final temperature. So we don't know what the final temperature is. So that's going to be left as unknown for now. And we need to change our delta T into F, our temperature F, right, which would be our final. And we know what our initial is. It's 1 degree. So instead of writing Ti for our temperature initial, we can just put 1 degrees Celsius. And then we have to add our addition of heat. How much heat got added in? Well, it says 4 kilojoules. That is going to give us a problem because if we have kilojoules over here, we look at our chart in order to cancel out our units properly, we're going to be running into joules. So rather than keeping it at kilojoules, we'll just change it right away to joules. So instead of 4 kilojoules, we'll have it at 4,000 joules. So let's add that here for our last factor. So we have 4,000 joules is equal to 1,000 grams times 4.19 joules over grams times Celsius times TF minus 1 degrees Celsius. Now we're just going to cancel out our units properly. We want our TF to be isolated alone. Right now it's not alone. It's stuck not only with this 1 degree Celsius, but it's also stuck with these two things. So let's first get rid of these two things. So right now we have 1,000 grams and 4.19 joules per gram Celsius. We're just going to divide them both. Cancel them all out. But if we do it on the right side of the equal sign, we need to do it on the left side of the equal sign. So let's do the same thing over here. Just going to bring this all over here then. So we are now left with our TF minus 1 degree Celsius is equal to our 4,000 joules divided by our 1,000 and our 4.19. However, it's going to look a little bit messy that way. So let's elongate it out so that it just looks a little bit cleaner. And we're just going to divide it this way. So we're going to divide it by our 1,000 grams and our 4.19 joules per gram Celsius. Now it looks a little bit more cleaner. Now we could pretend that this is a fraction. It's all over 1. So if you want to flip this and then change this into a multiplication, we could do that. Change it into a multiplication. So instead of 1,000 grams on top, it'll be on the bottom. And then this one here as well, it's going to be flipped. And it's going to equal TF minus 1 degree Celsius. And again, this is all over 1. So if we look at our units that we can cancel out, this is diagonal with this one, so this cancels out. This here is diagonal with this one, so this one, they cancel out. And then you're just left with your TF minus 1 degree Celsius. 4,000 times 1 times our degree Celsius, all over 1,000, times 4.19 and times 1, but you don't have to add it there if you don't want to. Let's just do our math here quick. We're just going to do our math quick over here. So 4,000 divided by 1,000 times 4.19. So you end up getting 0.9546. 0.9546. And that's going to be in degrees Celsius. So all we're going to do is try to isolate this TF here. So we're just going to do the opposite sign of -1 degree Celsius. So if it's -1, we're just going to plus 1 degree Celsius. So then these cancels out. If you do it on the right side, you have to do it on the left side. So we can just do it over here, plus 1 degree Celsius. And then our TF, you just add them together, you just get 1.95. This here is our value. Now let's look at this last question. The energy produced by burning one 0.25 gram candle releases enough heat to raise the temperature of 800 grams of water. So this is important, right? This is what we're going to use as our mass, because that's the one that's taking in the energy, absorbing that heat, right, endothermically, by 50 degrees Celsius. Okay, calculate the amount of energy that will be possible by burning this much of a candle after. Well, we got to do our initials first, okay, so that we can eventually figure out how much this one would be in terms of energy, so that we can equate it with a proper ratio with a candle that is much bigger. Let's put our Q is equal to MBC, MCT, like always. And our Q value, do we have our Q value? We have no idea. It even says that it's calculating the amount of energy, so we have no idea. We're just going to leave it unknown. Our mass, what is our mass going to be? It's quite obvious. It's going to be 800 grams. So let's write that there, 800 grams. Our specific heat capacity, we just look at water again here as 4.19. So it's 4.19 joules per gram Celsius. And then we're going to look at our temperature. Well, our temperature, what does it say? It raised, right, the temperature by 50 degrees Celsius. So it already gave us the value. So we don't need to do any final versus initial calculations. They've already given it to us. So it's just 50 degrees Celsius. We're just going to look for the value here. Again, this here is opposite, right? This is technically a fraction. It's over 1. So diagonally, these will cancel out. Again, this is also over 1 as well, technically. So this and this are diagonal, so they cancel out as well. So all we have to do is multiply them together. So let's do that together. 800 multiplied by 4.19 multiplied by 50, and then you get 167,600 joules. Now that we have that, this is our value for our 0.25 gram candle. But we're trying to look for 2.35. How much bigger is this 2.35? Well, a simple way is just get your bigger value and you divide it by the smaller value, and then you can pretty much find out how much bigger that is. So you just do 2.35 divided by 0.25, you get 9.4. So you just get 9.4 times bigger. So this value here, we just have to multiply it by 9.4. So our Q is equal to 167,600 times 9.4. I end up getting 1,575,440. This is what I have in joules. So this should be the answer, the amount of energy for that candle. These are the green questions of the day. So these are two different types of questions. So this is question 1 and this is question 2. Please give this a try. I'm going to be showing you the answer shortly. So I recommend pause the video, try your best to see what answers you get, and then check with the answer key that I'm going to be presenting to you. This is the answer for the first question. This is the answer for the second question.